Hi everyone. So now we will be going through the problem number 1 on beam element. So the problem says that there is a simply supported beam. Simply supported beam means one end will be a hinged support, another end will be a roller support. So this will be simply supported beam. On that there is a uniform distributed load. This we can see uniform distributed load. So in this we need to obtain the maximum deflection. So we need to consider Young's modulus as E is equal to 200 gigapascal. Moment of inertia is also given as 2 into 10 raised to 6 mm raised to 4. So the value of the UDL which is applied here is 12 kilonewton per meter. So first step is to convert all the units into meter and kilonewton, because here it is mm raised to 4. We need to convert this into meter raised to 4, and this we need to convert into kilonewton per meter square per meter square. So first Young's modulus will be converting into kilonewton per meter square. I also will be converting to meter raised to 4. So if you multiply EI, then we will be getting 400 kilonewton meter square. So first step is to write the given and convert all the units. So if you see the solution, as we have seen in many FEM problems and all finite element method problems. So first step is to draw the finite element model of the beam. So finite element model of the beam is like this. So this is first node and second node, where there will be theta 1 v1 and v2 theta 2. So the distance between these two nodes is 1 meter. So what we have done is we have written the finite element model. This is the first step in solving the problem. So the second step goes like this. We will be finding the elemental stiffness matrix. Already we know the stiffness matrix equation, that is EI by LE cube, and this equation, this matrix whatever is there, this we need to write down. This is nothing but the elemental stiffness matrix of a general beam. So we need to substitute all the values of LE here, LE and EI here. EI already we found out there, that is 400 we got, and L is nothing but length of an element, and there is a one element here. There are no two elements, only one element. That is why the value of this is 1 meter. Substitute wherever there is LE or L, substitute there as one value, 1 meter. So what you will be getting here is this matrix. Wherever there is L, we have substituted 1 here. So this is of the form matrix V1 theta 1 V2 theta 2, and here also it will be V1 theta 1 V2 theta 2. So this is of 4 into 4 matrix. So first step is we found out we have written the finite element model. Second step is we have found the stiffness matrix of this particular beam element. So the next step is, the third step is to find the global nodal displacement vector. So Q is nothing but V1 theta 1 V2 theta 2. So these are the things which we need to find out. Clear? These are the things which we need to find out. Nothing is known in this. V1 is also not known, theta 1 is also not known. Similarly, V2 and theta 2 are also not known. The next step is to find out the global load vector. Already we know the equation of the load vector when there is a UDL, that is uniformly distributed load. So the equation says F is equal to P naught LE by 2. Similarly, P naught LE square by 12 and P naught LE by 2. P naught. So in this, P naught is already given, that is minus 12 kilonewton per meter. Why minus? Because it is acting in the downward direction. Here also you can see P naught value we have taken it as minus because it is acting in the downward direction. You can see here UDL acting in the downward direction. That is why we have taken P naught as minus 12 kilonewton per meter, and length is already known, that is 1 meter. So by substituting this P naught and this LE, we will be getting this matrix minus 6, minus 1, minus 6, 1. So after that we go for standard equation, that is equilibrium equation, we go for that. So what that equilibrium equation says, K into Q is equal to F. So already stiffness matrix K matrix is known, Q matrix is also known here, that equation, and next F matrix is also known here. So substituting all these found out values or matrices in this standard equilibrium equation, that is KQ is equal to F. So after that, next step is important step where we apply the boundary conditions. In this, while applying the boundary conditions, we need to see how this exactly beam is given here. Boundary conditions are nothing but here it is a hinged where this V1 as well as theta 1 are 0. Similarly at node 2, at node 1, I repeat, at node 1, V1 which is acting in the upward direction is 0 and theta 1 due is a rotation, that is also 0. At node 2, V1 is free, no, V2 is also 0 because it is acting in this direction, it is 0. Only the rotation here theta 2 is available. Clear? That is why in the boundary conditions what is stored is V1, theta 1 and V2 are 0. So by applying these values, by putting these values in the equation, so what happens is V1, theta 1, V2, these three will be 0. That is why respective nothing but first row and first column will be eliminated. Similarly, second row, second column will be eliminated. Next, third row, third column will also be eliminated. I repeat, first row, first column because V1 is fixed. Next, theta is fixed. That is why second row, second column is also eliminated. Next, V2 is also 0. That is why third row and third column is eliminated. So left is which one? Only 4 into Q2, sorry, 4 into theta 2 is equal to 1 is left out. Clear? 1, 2, 3 are eliminated, nothing but 3 rows, 3 columns. First row, first column, second row, second column, third row, third column. So left out is 4 into theta 2. Clear? 4 into 400 into theta 2 is equal to 1 is the equation which is left out now. So here is what you will be getting. Nodal displacement vector Q is equal to 0, 0, 0. So to find out theta 2 is the equation 4 into 400 into Q, theta 2 is equal to 1. So theta 2 you will be getting is 6.25 into 10 raised to minus 4 radians. So that is the rotation you will be getting theta 2 value. So this is the answer. So in the question what is asked is to find the maximum deflection in the beam. So maximum deflection for this simply supported beam is at the center. So here is the maximum deflection. So what is the length now? It will be 1 by 2 for the beam. So we will be coming to find the required quantity now, that is to find the maximum deflection that is at the midpoint. So to find the maximum deflection, V is equal to H into Q. So what is H into Q? H1 into V1. So H is H1, H2, H3, H4 and Q is V1, theta 1, V2, theta 2. Already we know theta 1, V1 and V2 are 0. Theta V1, theta 1, V2 are 0. Only left is theta 2. That is why what we will be doing is this V maximum will be equal to LE by 2 H4 theta 2 because V2, theta 1, V1 are 0. Here you can see. By substituting H4, that is Hermite shape function in terms of zeta, shape function in terms of zeta. So substitute the value of zeta. So what will be zeta at the midpoint of the beam? For this simply supported beam, zeta will be 0. So substitute zeta as 0. Here also 0, 0, 0. So left out is minus 1 by 4 into theta 2 is also known. So what you will be getting is maximum deflection of 7.8125 into 10 raised to 5. 10 raised to minus 5 meter is the solution, that is maximum deflection. Where it is at the half of the beam, midpoint of the beam. And at the midpoint of the beam, zeta value is 0. That is why we have substituted zeta as 0, and theta 2, which we have found out already. That is theta 2 is 6.25 into 10 raised to minus 4. So V max, that is maximum deflection at the end, will be this value. Thank you.